pendulum of dynamic interactions. A pendulum is a physical system with a mass hanging from a fixed point by a string or a rod, and which can swing freely due to gravitational action. Any other interaction, such as a magnetic field or material elasticity, can also cause the pendulum to oscillate. The pendulum has been used in various ways since antiquity: time measurement, metronome, measurement of gravitational field strength, etc. Undoubtedly, the most popular application of the pendulum is time measurement. This application has its origins in the observation made by Galileo around 1581, when in the Cathedral of Pisa Galileo observed the movement of a hanging lamp. He looked at it and noticed something that caused him to repeat various experiments with pendulums, allowing him to confirm a phenomenon which showed that, although the amplitude of the oscillations was reduced, the oscillation frequency did not depend on the amplitude or the suspended weight, but only on the distance to the fixing point. This phenomenon was called isochronism and helped to give this researcher the intuition to develop his law of falling bodies.
At the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Later, Christian Huygens in 1656 repeated these studies and discovered that the period during which each length of suspended cord oscillated was constant. He concluded that, since small oscillations of the pendulum are isochronous, it was useful for measuring time. This led him to develop the pendulum clock, the most precise for calculating time, until the 1930s. Depending on their configuration and use, there are many different types of pendulums. They usually bear the names of their creators or their main feature: sample pendulum, cycloidal pendulum, double pendulum, Foucault pendulum, Newton's cradle, torsion pendulum, etc. Newton's cradle is a device that displays the conservation of linear momentum. It consists of a set of identical pendulums with solid balls as a suspended body, positioned so that the balls are perfectly and precisely horizontally aligned and just in contact with their adjacent balls when motionless. Each ball is suspended from a pair of wires of equal length so as to restrict the movement of the balls in the same vertical plane. Dropping a ball from one of the ends knocks the rest, transferring the amount of movement to the ball at the other end, which will shoot up, theoretically, to the same height as the initial ball, before falling subsequently by gravity and repeating the phenomenon from the opposite direction. This is how pendulum movement is started. A Foucault pendulum, named after its inventor, Léon Foucault, was used to demonstrate the Earth's rotation and the Coriolis effect, described in 1836 by the French scientist Gustave Gaspard Coriolis. This audiovisual document provides an outline of the behavior, from a mechanical and dynamic point of view, of a new pendulum. This is a device developed following the principles contained in the theory of dynamic interactions set out by Professor Gabriel Barceló in his publication Un Mundo en Rotación in 2008. We have not found any previous historical references for this pendulum. Hereafter we refer to this pendulum as the Pendulum of Dynamic Interactions, PDI, Thanks to it, we will carry out an experiment to demonstrate the principles set out by the theory of dynamic interactions. Let us briefly describe it. Like any pendulum, it has a suspension string. The body or suspension system is a gyroscope, a device consisting of two very different parts from a mechanical and dynamic point of view. 1. The stator. It is a rod which serves as the axis and is attached by one end to the pendulum suspension wire. The rod must be able to pivot freely on the union. 2. The rotor. It is a rigid body, ideally rotating, which rotates on the stator axis. The center of mass of the rotor must not be on the straight line of the suspension string. Gravitational interaction therefore provides torque to the rotor without the location of the point the rotor center will pivot and having any significant relevance. Theoretically and ideally, this rotation is completely inertial, without accelerations that force the rotor to increase or decrease its angular velocity. The pendulum of dynamic interactions is characterized by the fact that if the rotor has an angular momentum, the plane of the pendulum swing is not constant, unlike other pendulums. In the aforementioned text, Un Mundo en Rotación, Gabriel Barceló recalls his initial tests with a pendulum. In 1992, I began conducting experimental tests with simple pendulums supporting a gyroscope. If we maintain the gyroscope with its own rotation suspended from its axis by one of its ends, it will begin an orbiting movement. Besides the precession of the gyroscope, an unintended action is evident, since the pendulum no longer maintained the same oscillation plane, following a trajectory whose projection on the ground is a curved line. This reaction disappears if the gyroscope stops rotating, producing in this case the usual flat swing of the pendulum. He did confirm repeatedly that this pendulum, which he had designed with a rotating gyroscope, did not swing in a plane, and that the gyroscope modified its spatial position as soon as it started its intrinsic rotation. He added, "In a gyroscopic conical pendulum, movement is not limited to a plane, as the gyroscope that constitutes the weight follows a trajectory in space even without the initial momentum." It was also obvious that this was not the Foucault pendulum case, and therefore a change in the trajectory was not due to the movement of Earth's rotation or any other external agent. There was a clear cause and effect between the rotation gyroscope and its trajectory. This could be proof positive that orbiting and rotation were not independent, so they should not be treated as such. We analyzed with interest the behavior of this pendulum. Initially, Barceló thought about the possible existence of a central force that generated the trace in space, and not constantly in a vertical plane, and even if it was due to an external agent, so he expressed in his book. However, we had to determine its true cause. For example, if air resistance, the Magnus effect, or another aerodynamic effect generated this force. For our purposes, it was sufficient to consider the projection of the pendulum motion of the gyroscope on a horizontal plane, the shadow cast on the ground due to the effect of light from the ceiling on the gyroscope. Let us fix, within this plane, the origin of our coordinate system on the point of equilibrium of the pendulum, more precisely, on the shadow of this point. The movement of the shadow of the pendulum is the same as that of a point mass on the plane under an attractive force. After repeating the experiment with a simple steel ball suspended by a rope and provided with intrinsic angular momentum, he came to the conclusion that The force due to the Magnus effect is insufficient to move the steel ball with the anticipated result, and obviously it did not justify the obtained result. Having discounted the Magnus effect, or any other external agent, he thought that there was not any kind of outside force that could generate the obtained trajectory in this pendulum, but, with its deviation still evident, Barceló concluded that there had to be other hitherto unidentified causes. However, there were also enough evidence to suppose that the precession was only generated by an inertial phenomenon of dynamic interaction, without the existence of a central force being a prerequisite. It was then necessary to devise a new dynamic model to justify this behavior. The actual existence of that inertial force had to be identifiable and measurable by the effect caused by the supporting rope. It could be conceived a new dynamic model in which the orbiting movement is generated directly by dynamic interaction, by a coupling between the linear speed of the trajectory of the center of mass of the pendulum and its intrinsic rotation. The existence of a central force was not a prerequisite in this hypothesis, despite the apparent motion induced by a force of this kind. It was necessary to confirm whether it was possible to generalize the inertial behavior of rotating bodies. This intuition, watching that pendulum suspended with a gyroscope in rotation, allowed him to develop the theory of dynamic interactions. This theory uses the theory of fields to explain this phenomenon and interpret other multiple phenomena of rotational dynamics. In the system studied, we have all necessary ingredients required by the theory of dynamic interactions. A main angular momentum on the rotor part of the hanging body, a secondary torque which is driven by gravity, a rectilinear momentum, inherent characteristic of any hanging body in any functional pendulum. Therefore, Barceló could watch how the oscillating mass exhibited a variation in its initial rectilinear momentum in terms of direction. This is due to the fact, according to the theory of dynamic interactions, that the field of anisotropic velocities generated by the so-called secondary torque, the weight of the rotor in the gyroscope, is dynamically coupled with the translational velocity field, with the initial main angular momentum remaining constant. The observed curved path corresponds to algebraic sums of velocity fields, whereby we observe a swinging pendulum in space but not in a constant plane. Due to the natural effect of dynamic interactions described by the theory of dynamic interactions, we are looking at a behavior that bears no resemblance to any other pendulum in history. The pendulum of dynamic interactions, discovered by Barceló, shows a peculiar behavior, its center of mass marking a special trace that can be justified by referring to the theory of dynamic interactions. This theory holds that a dynamic coupling between the translational velocity field and the anisotropic velocity generated by the non-coaxial force will occur. This field overlapping will produce a new curved trajectory of the center of mass of the body, equivalent to that exerted by a central force without the existence of it. Through his studies and trials, Barceló has come to realize that the observed behavior in this pendulum can be generalized to all free bodies in space that have intrinsic angular momentum and rectilinear translational motion, linear momentum, when they are subjected to new torques or new non-coaxial forces with existing angular momentum. This behavior even represents evidence of a possible transfer of rotational dynamic energy to translational dynamic energy or vice versa. In the event that the acting torque is constant, as in the case of gravity, the deviation will also be constant, obtaining as a trajectory a closed orbit that turns into a spiral caused by friction with the Earth's atmosphere. This was how Barceló also became convinced that, in nature, bodies that orbit also rotate, with a mechanical correlation existing between both natural phenomena.